Okay, guys, so we'll do problems from this chapter. This says an elevator filled with passengers has a mass of 1700 kgs. The elevator accelerates upward from rest at a rate of 1.2 meters per second square for 1.5 seconds. Calculate the tension in the cable supporting the elevator. All right. So again, in all these problems, we're applying Newton's 3 laws. Okay. So the elevator is the object of interest. Here are the two forces acting on the elevator. Okay, the tension and mg, and in a lot of cases, the object will be moving in one dimension. Okay, so we'll choose one direction as positive. So we'll choose this as positive. So the net force, we are doing Newton's second law. Newton's second law says net force is mass times acceleration. Okay. So the net force in the upward direction is that. And they give us the mass and they give us the acceleration. Okay. So the tension is mg plus a. Okay, so you see when you're accelerating upward, the tension is greater than the weight of the object. That's the weight of the object. Okay, and the tension is greater than that. Okay, so if at all the cable breaks, that's when you'll break. When the acceleration is upward. Okay. Is there any other time when the acceleration would be upwards? Okay, when it's coming down and slowing down, the acceleration will be upward. Okay. All right. So calculate the tension in the cable. The tension is, and again, I will do it like this, 2 meters per second square, and divide by 9.8 times g. So we've gotten in the habit of doing that, and you'll see in a second why. So that's 0.122. So this is equal to mg plus 0.122 g. And if you want, now you can put in the mass of 1700 kg and g is 9.8. The reason I did this is, see, the tension is 12% greater than the weight of the object. Okay, 112% the weight of the object. Yes, so that's the tension. All right, so it accelerated for 1.5 seconds. The elevator continues upward at a constant velocity for 8.5 seconds. What is the tension in the cable during this time? Okay. So for the next 8.85 seconds, 8.5 seconds, what is the acceleration of the?
Gravity.
Very good. Okay, it's moving at constant velocity. Okay, so when it's moving at constant velocity, the tension is just mg. See, 12% less than when it was accelerating. Okay. All right, so when it accelerates upward, it can happen in two different instances I told you about. Okay, that's when the cable will snap if it does. The elevator decelerates at a rate of 0.6 meters per second square for 3 seconds. What is the tension during that time? Okay, so now there's the tension, there's mg. It's decelerating. The acceleration is that way, and that's okay. So we've been choosing this direction as positive, which we'll do, and so acceleration is negative 0.6 meters per second squared. Okay, and again I'm going to write it like so, because you guys understand when I do this? Okay. Everybody? Okay. You guys understand that makes more sense than just numbers. I can put a big number and it'll be meaningless. Okay. So you see, when it's decelerating, the tension is less than the weight. Okay. Is there any time when the tension would be zero?
If the cable had slack,
Yeah, very good. And when would that happen?
if the elevator was on the floor.
I'm sorry?
If the elevator was on the floor, or,
Yeah,
so, most likely
in free fall. If it was just dropping, okay, then the tension would be, when this was 9.8. Okay. All right. How high has the elevator moved above its original starting point, and what is its final velocity? Okay. So now this is part 2 of the problem. All right, so we're going to start off at rest, then for 1.5 seconds, we're going to accelerate at 1.2 meters per second squared. Okay, so what we want to find is how high has it climbed. Okay. All right, so at each point we first want to calculate the velocity. Okay. Okay, so we want to calculate the velocity here. We'll call this V0, V1, V2, V3. Okay. V1 equal to V0 plus AT, and I'm just going to write all this stuff quickly. Okay, so when you reach here, you're going at 1.8 meters per second, and then you continue at constant velocity. Okay, and also I'll call this D1, D2, D3. Distance traveled in the various legs. Okay, so we'll calculate D1, x minus x naught equal to 1/2, equal to V naught t plus 1/2 AT squared. Okay, so this is D1 equal to 0 plus 1/2 1.2 times 1.5 squared. Okay, so when it was accelerating, when it's speeding up, it speeds up for a distance of 1.35 meters, which is a little less than your height. Okay, so that's how fast, how much the elevator accelerates. Okay. Then D2 is, it's just going at constant velocity, so it's V1 times time. It's the constant velocity times time, and it was going at 1.8 meters per second for 8.5 seconds. So these are, again, as engineers, you have to think about this. 2 meters per second, 10 meters per second is about 25 miles an hour. This is 5 miles an hour. In some of the tall buildings nowadays, they have elevators that go at 50 miles an hour. 10 times the speed. Okay. Has anybody been in one of those elevators? Super fast elevators? Have you? Where?
I mean, I don't know a specific building, but I've been to like some of the tall spots in, like I went to Toronto and I went up to tower that's there, but I don't know how fast that elevator goes.
Yeah. All right, so D2 is 15.3 meters. And now we'll calculate the final distance D3. Okay, again, initial velocity is 1.8 meters, and now it's slowing down. Okay, before we do that, let's calculate the final velocity, V3. It'll have stopped, but let's make sure of that. Okay, V3 is equal to V2. And again, this is the final velocity, this is the initial velocity, plus A times T. So V3 is, initial velocity is 1.8, acceleration is 0.6 meters per second square, and T is 3 seconds. And so, as we had guessed, the elevator is stopped there. Okay, let's calculate the distance. V2 is the initial velocity plus 1/2 AT squared. We call this D3 times T, 1.8, 3 seconds, plus 1/2, negative 0.6 meters per second square times 3 seconds squared. So the distance covered there is 2.1 meters. Okay, so the total distance covered is d1 plus d2 plus d3. Okay. So during the acceleration phase, you covered, what distance did you cover? 1.35 meters. The constant velocity phase, you went 15.3 meters. And during the stopping phase, you covered 2.1 meters. Okay, 17.4, 18.75 meters. Okay, 18.5 meters is roughly a floor, so this is probably a 4-floor building. Okay. You guys understand that? Yeah. Yeah. So, do you guys know what an accelerometer is? It measures acceleration. Your phone has one. Okay, here's a simple way to do it. You can hang something heavy from your rear view mirror in the car, and that will be an accelerometer. Okay? And this problem illustrates that. So a 20-gram ball hangs from the roof of a freight car by a string. When the freight car begins to move, when the freight car accelerates, this is not likely, but anyway, here is the problem. So it makes an angle of 35 degrees. Okay, and we'll call that theta. With the vertical, what is the acceleration of the freight car? So they want you to find the acceleration of the freight car. All right, so I'm going to just draw the string. Okay. We'll call this theta. What is the other force acting on the ball?
Gravity.
Gravity. Okay, so this angle is theta. So this component of the tension is balancing the weight, and this component of the tension is making the ball accelerate in this direction. Remember, the ball has the same acceleration as the freight car. Okay? So T cosine theta equal to mg, and T sine theta equal to m times a. So if you divide this equation by that, you get tan theta ma by mg. So the acceleration of the freight car is g tan theta. So you see, you measure theta and you know the acceleration. Okay? So this is an accelerometer. What is tan 0?
0.
0. Tan 0 is 0. So when you're moving at constant velocity, the ball would hang straight down. What is tan 89? What is theta in the limit theta going to 90? What is tan? Infinity. Tan 45 is 1. Okay. So you can have an infinite acceleration, and that's when the ball will be horizontal. Okay. So it happens for Superman. Yes. So, and then you can calculate the tension when. Okay. So the tension is. I'm not doing the numbers. You guys can do the numbers. You can put in the numbers. Tension is mg divided by cosine theta. Now, m is 20 grams. Actually, I'll do it like so. So tension is 22% greater than the weight of the object. Okay? All right, any questions on that? A roller coaster car starts from rest at the top of a track 30 meters long and inclined at 20 degrees to the horizontal. Assume that friction can be ignored. Okay, so we'll call it theta, and theta is 20 degrees. The track is 30 meters long. What is the acceleration of the car? Okay, so it's a frictionless track. So essentially you can think of an ice cube sliding down this thing. Anybody remember what the component of the acceleration is down the incline?
Or mg sine theta.
Very good. So acceleration is g sine theta. Okay? So acceleration is g sine theta, g sine 20. One-third g. Okay. And how long does it take to reach the bottom? So we'll draw our x-axis this way. X minus x naught equal to v naught t plus 1/2 8t squared. Okay. It starts off at rest. This is 30 meters. 1/2 acceleration is 0.34 g t squared. Meter of an incline would be, see, from that corner to that corner. Okay, so if you let go of an ice cube at that corner, let's see how long it'll take. .24 seconds. Okay. Anybody remember what this is? It's an Atwood's machine. What was its purpose? What did it do?
It slowed down the acceleration of the
Very good. So
heavier object.
yeah, if this guy is heavier than that, this will accelerate downward, and depending on this mass, you can make that acceleration anywhere from g to 0. That's the idea. How do you make it g?
Have no counterweight.
Have no counterweight. M1 is 0 is g. How do you make it 0?
Make them equal.
Make them equal. Okay. So as this thing goes from 0 to M2, A goes from 0 to G, okay, or G to 0. All right, so that was the idea, and we will do this experiment in lab, okay? All right, by the way, for those who came in late, I'm going to be out of town Thursday. There's no class Thursday, and so there's no lab this week, okay? Yep.
Is there still a talk Thursday?
Yeah, there is a talk Thursday. Yeah, thank you. All right, so there will still be extra credit. It's again, a professor from UF, and he's going to talk about emerging diseases. Yeah. Who all are interested in the medical field? Yeah, I should go. Okay. Everybody should go. So they say for part A, find an equation for acceleration of the two blocks. Okay. So so we are assuming M2 is greater than M1, and we'll apply Newton's second law for each one of them. Okay, so the tension in the two strings is the same. When is the tension in the two strings the same? I'm sorry? Very good, my friend. Very good. So soon as you write that, what you're assuming is this pulley is massless and frictionless. Okay? All right, for the mass 2, the equation is M2G minus tension equal to M2 times A. For mass 1, we choose that direction as positive. T minus M1G equal to M1A. Okay, what we'll do is we'll add equation 1 and 2. If you add these two guys, see, the reason for adding that is the T will drop off. Okay. So here is the acceleration. And as we had said, when M1 equal to M2, when these two masses are equal, A is 0. And when M1 is 0, when this guy is 0, this guy will free fall. His acceleration would be, when this is 0, A would be equal to G. Okay. So based on this mass, you can dial the acceleration to any value you want. So part B says find the tension so you can use either one of these equations. Tension is M1 plus M2, M1G plus M1A. Let's see if we can simplify this. G M1 1 plus M2 minus M1. There's the tension. All right, let's make sure. So when M1 is equal to M2, when M1 is equal to M2, what is the acceleration? 0. If the acceleration is 0, tension is equal to M2G, right? So let's make sure that when M1 is equal to M2, that's 2M2 square. That is 2M2. The M2 cancels. The 2M2 cancels, you get M2G. Okay? All right, so get in that habit of checking your answer. Did you guys understand that? Let me do that again. Okay, so tension should be equal to M2G when M1 is equal to M2. So tension is 2M2 square divided by 2M2. Yep. All right, I'll leave it. So we have the tension. So there's the expression for the tension. And then part C, find both the acceleration and tension when the blocks have these masses. You guys can substitute that, okay?
And these equations are constant for all Atwood's machines, assuming friction is pulling.
Mhm. Okay, so a 2 kg block and a 4 kg mass are connected by a light string as shown. The inclination of the ramp is 40 degrees. Friction is negligible. What is the acceleration of each block? The tension in the string, okay? So this is, do you see any relationship between this guy and that guy? I'm sorry?
They're both using the same principle, you're just including.
When this angle becomes 90 degrees, this guy becomes that guy. Okay? So we'll derive, did you guys understand that? Okay, so we'll derive the equation putting theta, and when theta equal to 90, we should get the expression for the acceleration in the other guy. Okay? All right, again, we'll apply Newton's second law for this mass and for this mass independently, okay? So, again, tension is equal. What we're saying is this pulley is massless and frictionless, okay? M1G, but what's relevant is this is M1G sine theta. Okay. So M2G minus tension equal to M2A. T minus M1G sine theta equal to M1A. Okay, again, we'll add the two equations. The tension will cancel. right, so let me compare this to the equation for the Atwood's machine, the acceleration. See, there is the expression. And see, the acceleration is almost the same except that there's the sine theta there. Okay? And like we said, if theta becomes 90, sine theta is 1, and this expression reduces to that. Okay? So pretty neat. And then they want you to find the tension in the string. So you guys can substitute the numbers there, okay? The tension, you can use one of these equations. So the tension is m1g sine theta plus m1a. Okay. I'll just leave it like that because it probably will be very messy. And it won't do us any good. Okay, you just put in the numbers. A contestant in a winter sporting event pushes a 45 kg block of ice across a frozen lake. So he's pushing it down like that. Okay, so this horizontal component is F cosine theta, and the vertical component is F sine theta. So calculate the minimum force he must exert to get the block moving. Okay, so the force he must exert, this F cosine theta should overcome Fs max, okay, to get the block moving. What is Fx max?
It's the coefficient of static friction times.
The maximum static friction force. Okay, that's the force you need to get the block started. Okay, and Fs max is mu s times the normal force. Okay, in this case, you see mg. There's two forces acting down, mg, and then you're pressing down on it. So the normal force is balancing that. The normal force is mg plus F sine theta. So Fs max is mu s times mg plus F sine theta. Okay, so when the block just moves, F cosine theta equal to Fs max, F cosine theta equal to mu s times mg plus F sine theta. We have to solve for F is what we have to solve for. Calculate the minimum force F he must exert to get the block moving. Okay. So F cosine theta minus F times mu s sine theta equal to mu s times mg. So I'll show you something. All right. So we'll put in these numbers, mu s cosine 25 minus let's see if we can make sense out of this. Okay, what is coefficient of friction for ice on ice?
0.1.
Okay, so all right, so here's why I did this. Okay, so if you're pushing horizontally, the force you have to apply is Fs max is just mu s times mg. Okay, mg is the weight, and that's the normal force. Okay, now by pushing like this, what you have done is you're pressing down the ice on the lake surface, and this friction force has increased by 15%. That's effectively. It got harder to push. Did you guys understand that? That's what happened. What if you push straight down? Will this guy ever move? No. Okay. So when you push horizontally, that's when it's easiest to move, and as you're increasing the angle, it's getting harder and harder to move. Okay. All right, this time we'll put numbers. I'll show you part B. Okay. What is its acceleration once it starts to move? What will change once it starts to move?
Coefficient of friction.
Yep. So now you have to use mu k instead of mu s. And what about mu k?
It's a 0.03.
Yeah, so mu k is always less than mu s. Okay, so that once it starts moving, the friction decreases. Okay, or it's less than the maximum friction. Okay. I guess we'll need this F, so we'll have to calculate this. Okay, I'm going to erase this. F is 1.15 and mu s was 0.1 and mg 45 kg. Well, we'll keep mg. Okay, so we're going to apply the same F. Okay, and except that now this is Fk. So F cosine theta, and remember theta was 25 degrees. Yeah. The normal force was balancing this and that, and that's what that is. All right, so now I'm going to put in the numbers, the acceleration. So F is 0.115 mg cosine 25, and what did you say mu k was?
0.03.
0.03 mg plus 0.115 mg sine 25 equal to m times m. So essentially this works out to 0.0101 mg equal to m times a. Acceleration is 1/10 g. Okay. So the mass canceled out. That means all blocks will move at that acceleration. All right, let's do this one and then we'll go to that one. Calculate the velocity of a spherical raindrop. A spherical raindrop would achieve falling from 5 kilometers in the absence of air drag, okay, with air drag. Take the size across the drop to be 4 millimeters. The density of water is of course that, and the surface area to be, not the surface area, area of cross section. Surface area of a sphere is 4 pi r squared. All right, so for part A, you're going to fall, and there's no air drag, so you're going to accelerate at g. Okay, so this will be final velocity. This will be initial velocity, and x minus x naught is 5 kilometers, which is 5,000 meters. So v square equal to v naught square plus 2a x minus x naught. This is 0. You're starting off at rest when you start falling from the cloud. So v is 2a x minus x naught. So this would hit the ground at 313 meters per second. 10 meters per second is 25 miles an hour. So this would be 30 times 25, 750 miles an hour, Mach 1. You wouldn't be walking in the rain. So thank goodness for air drag. Okay. So now we'll calculate the velocity with air drag present. Okay. So let's look up the expression for air drag for terminal velocity. Okay, so here's the expression for terminal velocity. 2 mgc is sigma rho a. Okay, so rho is the fluid through which you're falling, and you're falling through air. Here's this area of cross section is A. Okay, and by the way, the mass of the drop is the density of the drop, density of water, times the volume of the water, R cubed. Okay, that area is equal to pi r squared for the drop. Okay, so let's plug all of that in. So the terminal velocity is 2 m is the density of water times 4 pi by 3 r cubed g c is not given. um, c will take to be half. Okay, if you look up your notes, c varies between half and 2, and for aerodynamic objects it's half. For for a for a semi blocky vehicle like a UPS truck and stuff like that, it'll be 2. So we'll be generous and take C to be half. Density of air by r squared. The pi cancels, r squared cancels. So terminal velocity is 2 times the density of water, 4/3 r g, 0.5 times density of air. Yep. All right, now let's put in the stuff. Density of water is 1000 kg per meter cube. That's given. 4/3 r, the radius they give you the diameter of the drop to be 4 millimeters. So the radius is 2 millimeters. And you can look up the density of air is 1.3 kgs per meter cube. Essentially, the density of water is 1,000 times greater. Okay. Okay, this kills that. So that becomes 2, 4, 16, 16 times 9 point. And 3 times that is 1.5. Hmm. Nine meters per second, which is about 25 miles an hour. Now, in this rain, you could walk. Okay. All right, so I'll do this from Okay, we'll do point A. At point A, the speed of the car is 10 meters per second. Is this guy accelerating? Why? I'm sorry?
Changing direction.
Right. Okay. And in this case, actually, the speed will also be changing, but right now, the velocity, the acceleration, the direction is changing. And what is the centripetal acceleration? It's v squared by r. R is the radius of the circle you're going. Okay? So to make him go in that circle, you need a force. You need this much force. You need that much acceleration, mass. Where is that coming from? Gravity is 1. So let's say gravity contributes that much. Well, you need a little more. I haven't done the numbers, but what if you need a little more? Then where are you getting that extra force from? This guy is pushing you. The track is pushing you down. And so they always design roller coasters such that at the top your speed is such that this acceleration is always greater than g. Okay, so you need a push from the track. And if this acceleration is greater than g, you need a push from the track. There's no way you're coming off the track. You don't even have to wear a seatbelt. You do, but I'm not encouraging you not to wear seatbelts, but that's how they're designed. And so I really don't understand how somebody falls off those things. There's no way you're supposed to fall off. All right. All right, so we'll look at that. Okay, so a child of mass 40 kgs in a roller coaster car that travels in a loop of radius 7 meters. So the radius of the loop is 7 meters. At point A, the speed of the car is 10 meters per second. At point B, assume the child is not holding on and does not wear a seatbelt. There you go. All right. What is the force of the car seat on the child at point A? Okay. So we'll calculate AC. AC is V squared over R, 10 squared over 700 over 7. And so as promised, that's greater than G. Okay. And how do they make sure that you're going that fast at the top? You just make sure that you release the person from a high enough spot. Okay? Yeah, or in this case, so you release the person from a high enough spot. Okay, so in this direction. All right. What is it that they're asking? What is the force, the car seat on the child at point A? Okay, so you see force of the seat plus mg is providing m times the centripetal acceleration. Yeah? So force of the seat is Okay, so the seat is having to push with a force of 45% the weight of the child. Okay, so what minimum speed is required to keep the child in his seat at point A? Okay. So here's, pay attention to this. Okay. So this, okay, this is not going to quit. Okay, actually, so let me write this equation down. The seat plus mg equal to mv square. Okay, so this guy is not going to quit. That's going to be there. This can go to 0. The seat can not push you. Okay. What if this number, if this is such that this number is smaller than that? Well, this has to be an equation. So then the radius becomes smaller so that this number is equal to that number. What does the radius becoming smaller mean? If you don't have enough speed, then you come off the track. That's what happens. Okay. So we'll calculate the minimum speed such that that is equal to that. For that track, .3 meters per second. So if you're going at least at 8.3 meters per second, you won't come off the track. Okay. So if you're going to design a roller coaster, what you do is, if you release from there, that's your speed, 8.3 meters per second. Okay. So what do? Because there are lawyers in the world, you release from at least 10 meters above that. Okay. You make sure that cart is going fast enough. Okay, and that's the idea.